Hello everyone. Today I will talk about Gen3DEval, a framework designed to bridge the gap between automated and human-aligned evaluation of text to 3D generated objects. In the next few slides, we will provide an overview of the paper. Traditional metrics such as CLIP and PSNR are either overly reliant on ground truth data or fail to capture the multifaceted quality dimensions required for evaluating 3D objects. Through our benchmarking experiments, we also noted that more recent metrics such as image reward and pic score were more attuned to the evaluation of images and not 3D objects. Alternatively, user studies are employed for this purpose. However, neither are they standardized nor are they time and cost effective. In contrast, we observed that task-specific LLMs demonstrated a basic understanding of objects in the language space, are good at instruction following, as well as making pairwise evaluations in other domains. This is the insight that Gen3DEval is built upon. So what is Gen3DEval? Gen3DEval is a vision-based large language model that is specifically trained to perform evaluations of generated 3D assets in a pairwise manner. For this purpose, it takes as input 4 multi-view images of the two objects, uniformly sampled from 360-degree videos, along with a question prompt which essentially asks the model to choose between the pair of objects. This can be on the basis of appearance, fidelity to text, or surface quality. The output of the model is its preference in the natural language format. Apart from the evaluation method, we also put together a benchmark containing 80 prompts that were curated to provide diversity of generation such as object type and composition, enabling granular evaluation while at the same time reducing the size of benchmark because 3D generation can sometimes be compute and time intensive. We also aim to increase the mean and variance of the prompt lengths. In the next few slides, we will discuss the methodology of Gen3DEval. The training process builds upon the Lava architecture and is split into two sequential phases, pre-training and supervised fine-tuning. In the pre-training stage, the objective is to train the projection matrix that aligns images with the language token space. First, the images are processed by a frozen image encoder to produce visual embeddings. This is CLIP in our case. The embeddings are transformed into vision language tokens via the aforementioned projection matrix, enabling them to seamlessly integrate with the language-based representations. At the same time, the natural language question-answer prompts are converted by a language tokenizer into text tokens. The model then receives both of them as input, learning to predict the next token by maximizing the likelihood of the correctly predicted next token. The LLM is frozen in this stage. In the supervised fine-tuning stage, the objective is to train the model in a task-specific manner. So both the projection matrix and the LLM are updated and fine-tuned on annotated pairwise comparison data. After training the model to compare objects with multi-view renderings, it is applied to compare outputs of generative 3D methods on our curated benchmark Gen3DEval bench, and further deriving rankings using the ELO rating system. A key aspect of the framework is the dataset. In the pre-training stage, the objective is to train a projection matrix to learn correlations between the image and language encoding space. Therefore, to train this, we use the renderings of 141,000 3D artist-generated meshes and their accompanying text prompts by sampling single and multi-view RGB and surface normal images and image grids. In the supervised fine-tuning stage, the projection matrix and language model are jointly trained with task-specific instruction-following question-answer prompts along with object comparison data. This data set comprises pairwise comparison data of 3D objects curated per the dimensions of appearance, text fidelity, and surface quality separately. They have been generated by various 3D representations such as meshes, Gaussian splats, and nerves, as well as by applying synthetic perturbations to simulate common artifacts observed in generated 3D assets such as smoothing, edge beveling, extrusions, etc. The supervised fine-tuning dataset also contains pairwise comparison data curated from user studies where users were shown 360-degree videos of two objects and asked to choose the object that they preferred. We will now discuss the results of Gen3DEval, first with other evaluation methods using quantitative metrics and qualitative examples, followed by a presentation of a leaderboard to rank methods on Gen3DEval bench. We report accuracy for curated synthetic and out-of-domain human preference evaluation datasets for appearance, surface quality, and text fidelity. On both synthetic and human annotated datasets, we observe that Gen3DEval outperforms other vLLMs as well as evaluation metrics, especially on appearance and surface quality. It also narrowly outperforms pick score and image reward on text fidelity. Here, we showcase a few qualitative examples of where Gen3DEval aligns with human preference data compared with other methods. We compared our method with evaluation metrics such as CLIP, image reward, and pick score, as well as our vision-based large language models such as GPT-4o, Lava Llama 8b, PaliGemma, etc. Finally, let's discuss applying Gen3DEval to Gen3DEval bench in order to compare generative 3D methods. In this table, we note the rankings of the methods that we were able to compare on all the evaluation dimensions. We added both text to 3D as well as image to 3D methods, which are the ones denoted with an asterisk next to their names. The overall ranking is calculated from the average of appearance and text fidelity scores. The number of methods will progressively increase in due time. In this slide, I have arranged some 3D assets per their appearance, text fidelity, and surface quality ranking as evaluated by Gen3DEval from left to right in a decreasing order of preference. We do have some limitations. For one, while we have curated text prompts for image to 3D methods, curation of a benchmark of image prompts with high quality images and possibly further disambiguating between text to 3D and image to 3D methods could be helpful. There is also room for improvement on the performance on surface quality dimension, and scaling up the data could help. The framework is limited by the capacity and context size of the base LLM, and finally, assessment of objects with Janus effects can be slightly erratic. In conclusion, we have delivered a human-aligned framework for 3D object evaluation called Gen3DEval. It incorporates 3D aesthetic preference into the vision language space by fine-tuning a vision-based large language model on annotated data, transforming that into a ready-to-use evaluation ranking metric. It sets a new standard in the field of text to 3D generation by being a holistic, automated, and scalable evaluation method, demonstrating strong 3D object evaluation capabilities of LLMs. Gen3DEval bench is a smaller and diverse benchmark that can be used to evaluate on appearance, faithfulness, and quality on a more granular level.